human body. Nothing we know of is as complex or finely tuned. How did humans reach this level of sophistication? The generally accepted explanation rules out a design or a designer. This series will challenge that assumption and will ask the hard questions about human development. In this episode, we'll look at how our bodies must overcome a life and death challenge from the unique perspective of an engineer and a physician. Dr. Howard Glicksman has been a medical practitioner for more than 45 years. He's an author and a speaker with a special expertise in why human systems succeed and why they fail. Steve Loftman is a systems architect with more than 45 years of experience designing enterprise-class systems of the highest complexity. He also leads a research group exploring the exquisite engineering found in living systems.
Whether it's a smartphone or a spacecraft, engineers know how to build amazingly complex systems, and we've all benefited. But it's become clear to me that nothing we've ever made comes close to the elaborate engineering found in our own bodies.
And as a doctor, I can tell you that engineering is undeniable. And that's from the whole body all the way down to the molecular machinery in our cells. But think about this. On a race car, just one tiny problem among its thousands of parts can cause a colossal failure. In the same way, our bodies have not thousands, but billions of parts that are incredibly fine-tuned. And the truth is that any one of a billion things could go wrong, any one of which could end your life.
One of the most serious ways your body can go wrong is not getting enough oxygen. Oxygen is essential for life. But as we'll see, to harness its power, your body requires astonishing engineering.
Starting at the most basic level, our primary human need is energy, and our cells are the power plants of the body. Within your cells are these high-performance turbine engines called ATP synthase. They make the energy packets that drive pretty much everything in our bodies, and there's upwards of 1 million of these in every cell.
They are very impressive machines, and they run continuously without a break.
Well, they have to for the cell to survive, which raises an important issue. ATP synthase can't do its job without oxygen, and it needs a continuous supply. But our bodies can't store oxygen.
Our bodies can store plenty of water and fat, but not oxygen. That's a problem because we have more than 30 trillion cells to oxygenate. Without an uninterrupted supply of oxygen, the energy turbines inside our cells will fail, and so will we. To keep us alive, we need to deliver oxygen to every single cell, every single minute of our lives.
And really, this is a much more elaborate problem than one might think. So let's take it on with an engineering perspective. Our main problem is every cell needs oxygen, but that brings up two more problems. First, most cells are in the interior of the body with no direct access to the air. And the second is that the demand for oxygen changes rapidly. So to solve these two problems, we need to solve 4 more problems. We need to get enough oxygen into the body. We need to absorb enough oxygen into the blood, deliver that oxygen in sufficient quantities throughout the body, and then regulate the oxygen delivery for rapidly changing local needs. So you can see there's a whole cascade of problems taking shape. And as we'll see in a little bit, it's a really long cascade.
And every one of them requires one or several solutions to keep you alive.
Now for a closer look at some of these engineering problems faced by the body. First up, how does the body solve the problem of getting oxygen into the blood?
So we obviously start with the lungs. They pull in air, which consists of about 21% oxygen, or O2. The heart sends blood to the lungs to pick up a fresh supply of oxygen. But how does the oxygen actually get into the blood? It's through the process of diffusion. The O2 molecules pass through these two thin membranes. There's a limit to how many can pass per second, but our body requires a minimum of 100 million trillion O2 molecules per second. At this rate, we'll never get the oxygen we need. A larger surface area will allow more oxygen in. But how much more area do we need? About this much, half of a tennis court. So there's an obvious problem. Our lungs are this size. To match that surface area, they need to be something like this size. How do we make that work? Well, instead of giant air sacs, we use super tiny air sacs. Actually, about 300 million tiny air sacs in each lung. They're called alveoli. They're surrounded by hundreds of capillaries. So the total surface area of the many alveoli meets the requirements for enough oxygen to pass from the lungs to the circulation. Problem solved. And here's what it looks like.
Millions of microscopic airbags increase the surface area and fit it into a much smaller space. This is brilliant engineering and brilliant packaging. And now the oxygen is in the bloodstream.
But now we have a problem that's even harder.
Oxygen molecules don't dissolve well in water, which is the fluid component of blood. This poor solubility means not enough oxygen can be transported in the circulation, and the bloodstream can't deliver enough oxygen to the cells.
So we need a transport solution for oxygen that can reliably reach each one of those trillions of cells.
And the solution to this one is in your bones. Here inside your bone marrow is a factory. It's where red blood cells are made. Manufactured within each blood cell are these incredible transporters called hemoglobin. Each one can onboard up to 4 molecules of oxygen.
It's like a micro 4-seater Jeep.
Yeah, ready to roll and deliver the oxygen. Each of these red blood cells has about 270 million hemoglobin molecules. And that means one red blood cell can carry a cargo of over 1 billion oxygen molecules to the tissues. So now, each one of our 20+ trillion red blood cells is equipped to carry oxygen to every part of your body.
But there is yet another challenge that has to be overcome. To carry oxygen, the hemoglobin in your red blood cells requires iron. The problem is that iron is toxic to the body, but hemoglobin can't be produced without it. So this calls for a supply chain that regulates a hazardous material.
This one is tricky, and to solve it, we need our digestive system. The liver is what monitors the iron we digest. And this is critical because if you can't regulate iron, you're dead. So the liver is in constant communication with the small intestine. It tells the intestinal cells how much iron to put into the blood. It can't be too much or too little. The liver also makes a transport protein called transferrin. Its job is to safely transport iron in your blood so it can't interact with any other parts of your body. Transferrin delivers it to the bone marrow, where the iron is used in making hemoglobin. This coordinated system controls the supply and delivery of iron while avoiding any toxic damage.
So we've cleared a lot of hurdles, and now the oxygen is being delivered to every cell. ATP synthase is churning away, and our cells have what they need to do their jobs.
Yeah, but we're going to need a lot more engineering to keep us alive. There's another extremely challenging problem. The body's energy needs are always changing. For example, when you suddenly realize you're going to be late to catch a bus, there's an immediate need for extra oxygen in your leg muscles. A burst of speed requires quick energy.
This problem is especially tough because it requires an extremely rapid response.
And we need yet another system to solve it, the cardiovascular system. When the body increases its level of activity, the brain sends a neural hormone that makes the heart pump harder and faster to send out more blood, which travels from the arteries to the arterioles to the capillaries, which feed the tissues. The arterioles are surrounded by smooth muscle that works like a valve, allowing more or less blood to flow. The arterioles in the leg muscles receive signals to open wider and provide more blood flow, while the arterioles to other organs, such as the gastrointestinal system, get the signal to close a bit and reduce the blood flow so more blood can be directed to the legs. This is why exercise sometimes causes stomach cramps. The increased activity of the leg muscles also causes a local buildup of CO2 and lactic acid, causing that thigh burn. This prompts those arterioles to open even more, and the leg muscles get that extra blood they need to catch that bus.
The problems and solutions we've seen only scratch the surface of the complex, integrated systems required for our bodies to use oxygen.
This is what we're talking about.
So what we see here is that every one of those problems leads to other problems that have to be solved. If any one of these problems is not solved, even for just a couple of minutes,
You're dead.
And that's just for respiration. There's thousands of other human functions that require a similar cascade of problems to solve.
The ways our bodies solve the challenges of using oxygen are eerily similar to the methods devised by human engineers to solve the problems they face. One method employed by human engineers are control systems. This one regulates the temperature in your home. It has 4 essential components. A sensor. Your thermostat recognizes a drop in temperature. Control logic. The control board determines the needed adjustment. Just-in-time signaling is supplied through a circuit. And what engineers call the effector is the furnace, which boosts the heat, usually without you even noticing it. Do we see this in the human body? Yes, in many places. For example, chemical sensors in the main arteries going to your brain monitor oxygen. Our control logic, in the brain, determines the needed adjustment. Just-in-time signaling is sent through our nerves. And the effector is supplied by the muscles of respiration. Again, without you even realizing it.
Human control systems are designed to be regulated with incredible precision, doing just the right things at just the right times in just the right amounts.
Another method used by human engineers is coherence, where each part of a system is designed to work with the whole. Each part is specialized, and then all the parts must be properly organized, integrated, and coordinated. And as we've seen in the human body, each of its coherent systems consists of the right size parts with the right shapes, made of the right materials, in the right places, coordinated just right to perform the right functions in the right order and at just the right times.
We've also seen many kinds of interdependencies, systems that cannot do their job unless other systems are also in place and doing their jobs. We can't oxygenate ourselves unless these 6 systems are in full operation. But each of these systems are made of cells, and those cells require oxygen, which none of them can get unless all the systems are in place. So this is a chicken or egg problem. Which of these systems could possibly have come first while the body remained alive?
Coherence and interdependence present causal hurdles, problems that can only be solved when many concurrent problems and subproblems and sub-subproblems must be solved, all at pretty much the same time. How is it possible for these systems to exist in the human body? When we see these kinds of engineering approaches used in daily life, they point to a human engineer as the ultimate cause. Do similar engineering approaches in our bodies point to a cosmic engineer. We're left with two options.
Did the human body result from a long, long series of cosmic accidents? Or was the human body intended?
And given what we've seen, which option is most likely?